Yeah. Inside the heart of the machine, where the circuits come alive, there's a unit on a mission, keeping systems running right. Arithmetic and logic, every function in its sight, processing the data in the billionths of a night. When the numbers start flying and instructions flow through, it's the ALU working, doing what it's built to do. Cause the ALU adds it up, breaks it down, keeps the flags in view, carry zero overflow, telling what is true, with the control unit guiding every move. Yeah, the system keeps running, all because of the ALU. AD and some operations coming through, CMP for comparison, no result, just a clue. And no XOR, test the bits one by one. Logic beats deciding what is 0 or 1. Multiplying, dividing, I'm all I veer and play. Registers in memory working day after day. Every clock tick matters when the processor runs. Fast decisions made before the next instruction comes, and the control unit signals where the data should move, keeping order in the workflow in a digital groove. Cause the ALU adds it up, breaks it down, keeps the flags in view, carry zero overflow, telling what is true, with the control unit guiding every move. Yeah, the system keeps running, all because of the ALU. Status flags lighting up inside, CF, ZF, O of nothing to hide. Parity sign, every result defined, truth in every output, logic aligned. Jumps and loops, program flow and control, the CPU deciding which direction to go. A new instruction enters, processed on cue, the control unit hands it off to the ALU. Cause the ALU makes the magic happen deep inside the CPU, fast as lightning, every cycle running through, with the control unit telling what to do. Yeah, computers keep thinking, all because of the ALU. All because of the ALU. All because of the ALU.
I hope you enjoyed our song, and for the simulation part, it will be firstly discussed by Mr. Fernandez.
This program demonstrates how the CPU handles addition and subtraction, and how it sets its flags after each operation. The code starts by testing simple addition cases. First, it adds two small numbers, 2 and 3, which produces 5. So we can see here, 5. Since the result is normal, no flags are raised, there is no carry, no overflow, and the result is positive. Next, the program adds 65,535 and 1. Even though the mathematical result is 65,536, the 16-bit register wraps around to 0. This causes the carry flag to activate, showing an unsigned overflow, and the 0 flag is also set because the result is 0. The third addition test shows signed overflow. Adding 1 to 32,767 produces negative 32,768 in a signed interpretation. Here, the overflow flag is set, and the signed flag indicates a negative result, even though there was no unsigned carry. After that, the program moves on to subtraction. It first subtracts 3 from 5, which results to 2 with no borrow and no overflow. Then it subtracts 1 from 0, causing a borrow. The result becomes negative 1, which sets the carry flag and the signed flag. Finally, the program demonstrates signed overflow in subtraction by subtracting 1 from negative 32,768. This produces 32,767, flipping the sign unexpectedly and setting the overflow flag. Each NOP instruction gives us a pause to inspect the registers and flags, making it easier to see exactly how the CPU reacts to each arithmetic operation. The next operation will be discussed by Choco.
Now, let's move on to the CMP instructions. In the CMP example, AX is 0005H or 5 and BX is 0005H, which is 5 also. Since the values are equal, the result is 0 and the 0 flag is set. Next, for the next example, AX is 0002H and BX is 0003H, which is 2 and 3. And because 2 is less than 3, the carry flag or CF is set, indicating an unsigned comparison. In the last test, AX holds 8000H, which is negative 32,768, and BX holds 0001H or 1. Comparing a negative and a positive number, sets and sign flags, showing how signed values affects flags. And why is CMP important? CMP is important because it allows the program to make decisions and branches without changing register values. Now let's move on to end and test. First off, the end instruction. Here, AX is 0F0F, which is a hexadecimal, and BX is 00FF. A bitwise end produces 000F, which is stored in AX, so you can see. And the result is a non-zero, so that the 0 flag is cleared. And both the carry and overflow flags are cleared. And this is important because it is used for masking bits, clearing unwanted bits, and preparing data for hardware or logical checks. Now, let's move on to the test instruction. In the first test example, AX and BX both contains 0002, which is 2, producing a non-zero result. So the 0 flag is cleared. And now, for the second test example, AX is 0004, which is 4, and BX is 0008, which is 8. Since there are no matching bits, the result is 0 and the 0 flag is set, as you can see. So why is test important? Test is important because it allows the program to check specific bits or conditions without modifying the original data. The next part will be discussed by Winsel.
For my part, I will demonstrate how the increment and negate instructions work in assembly using MO 1886. I'll focus on how they affect registers and CPU plugs, especially in special or edge cases, and why those plugs are important. Here, at our example, AX starts at 0. When I execute increment AX, the value becomes 0001H. Notice that the carry flag is not affected by increment. This is important because increment can be used in loops or counters without accidentally changing the carry flag, which may be needed for other calculations. For our next example, now, AX contains 7FFFH, which is the largest positive signed number. After incrementing, AX becomes 8000H. This causes a sign overflow. So the overflow flag is set. The overflow flag tells us that the signed result is no longer valid. Programs that work with signed numbers rely on this flag to detect errors or limit values. For our negate instruction, negating 0 still results in 0. Because the value is 0, the carry flag remains cleared. This helps the CPU distinguish between negating 0 and negating non-zero value, which is useful in arithmetic checks and conditional logic. So for our example, here, AX is 1. After negation, AX becomes FFFH represents negative 1. Since the original value was non-zero, the carry flag is set. The carry flag indicates that a real arithmetic operation occurred. Programs can use this flag to detect that negation was successful and meaningful. For the last, this is a special case. 8000H represents negative 32,768, which cannot be negated in 16-bit signed form. The result stays the same, and both the carry flag and over flag are set. This warns the program that the result is invalid. Checking the overflow flag prevents incorrect calculation and unexpected program behavior. So, this program shows increment and negation behave in both normal and edge cases. By stepping through the code in MO8086, we can see how CPU flags act as signals that help programs make correct decisions, detect errors, and control program flow. So, for the next part, it will be discussed by Mr. Fernandez.
This program demonstrates how the CMP and JMP instructions work together to control program flow. First, two values are loaded into AX and BX registers. The CMP instruction then compares these two values by internally subtracting BX from AX and updating the CPU flags. If the values are equal, the result of the comparison is 0, which activates the 0 flag, and JE, or jump if equal, instruction checks this flag and transfers execution to the value equal label. In this case, the program sets the CX register to 1 to indicate that the values are matched. If the values are not equal, the 0 flag is not set, so the conditional jump is skipped. The program then follows the default path using an unconditional jump to reach the not equal section, where CX is equals to 0. This example shows how CMP determines the condition and how JMP uses the result of the comparison to decide which path the CPU will take. Together, they form the foundation of decision-making in assembly language, similar to how an if-else statement works in high-level programming.
That's all for our presentation. Thank you for listening. Thank you.
Yeah. Inside the heart of the street, where the circles come alive, there's a unit on a mission, keeping systems running right. Arithmetic and logic, every function in its sight, processing the data in the billionths of a night. When the numbers start flying and instructions flow through, it's the air working, doing what it's built to do. Cause the air adds it up, breaks it down, keeps it back to you. Carry zero overflow, telling